Here we're going to look at Pascal's triangle. So this is kind of a really easy to generate triangle, but with some really cool patterns. So we call it Pascal's triangle, although it clearly was not first invented by Pascal. Like many mathematical things, the name gets associated, even though it had been around a long time before. But anyway, the way this works is we start at the top with a 1. And then below that, we have a row with 2 1s. And then basically we have 1s all along the diagonals here. And any number that we want to create from there on the inside, we just add the 2 numbers together above it. And so we would get 1, 2, 1. And then same thing if we want to get the next row, we're going to have 1s on the outside, but then we'll just add together these numbers here. So we'll say, okay, we start with a 1, we add 1 and 2 to get 3, add 2 and 1 to get 3, and then 1s again along the diagonal. So we get 1, then we get 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then 1 along the diagonal. So basically we just build this thing up, and right, we're always adding the 2 numbers above. And so we see there's definitely symmetry. We see that there are some clear patterns going on, like along the diagonals we said there are 1s, but along the next diagonal we see 1, 2, 3, 4, 5, right? And that's going to keep going mainly because we keep adding 1 to the number that came before it. So 1 and 3 made 4, 1 and 4 made 5, 1 and 5 make 6, and so on. But these numbers get really large, relatively quickly. And again, we just see the symmetry, which is going to play a role in a bunch of the patterns that we have. So I'll just do one more row of this, 35, 35, 21, 7, and 1, right? So we have a ton of patterns in this. We can use Pascal's triangle to take a look at powers of 2, something we call binomial coefficients, which is usually powers of binomials. A binomial is just, we see the prefix bi, right? That means 2. So basically a term with 2 or an expression with 2 terms in it, like x plus y. So this is a really common thing we do. We do things like x plus y to the 5th, x plus y cubed. You can also change these. You could say a plus b, or you could say x plus 7, or any kind of thing with 2 terms. Triangular numbers we can look at, Fibonacci numbers, which we have already looked at, and also combinations, which we looked at much earlier in the course. So let's start off. We're going to use Pascal's triangle to determine the values of 2 to the 0, 2 to the 1st, 2 squared, 2 cubed, and 2 to the 7th. Well, we might already know what these values are. So if you remember your exponents, anything to the 1st power is itself. So 2 to the 1st is just 2. Anything to the 0 power is 1. 2 squared is just 2 times 2, so that's 4. 2 cubed is going to be 8. And down the line, 2 to the 7th, let's see, I believe this is 128. So we're going to see if we can actually justify that using the triangle somehow. Well, how this works is we just look at the rows. So 2 to the 0 is just equal to 1. Our next one, 2 to the 1st, well, if we add up these 2 numbers, 1 plus 1, sure enough, we get what we assumed 2 to the 1st was going to be, which was 2. 2 squared, if I add up these numbers, 1 plus 2 plus 1, we're going to get 4, which of course is what we expected. And 2 cubed, we're going to add up 1 plus 3 plus 3 plus 1, so we end up getting 8. Right, which is, again, what we expected. So some of these other powers, though, like 2 to the 7th, most of you probably wouldn't know that offhand, right? 2 squared, okay, sure, no big deal. But 2 to the 7th, yeah, that's going to be a little bit wild. So we want to take a look and say, well, where would I need to go in this thing to find 2 to the 7th, right? I don't want to have to keep counting down. Okay, here's 2 to the 4th, 5th, 6th, 7th. But what we can do is we can take a look at one of these diagonals and say, oh, 2 to the 1st was here, 2 to the 2nd was here, 2 to the 3rd was here. So, okay, 2 to the 7th is going to be that second diagonal where we see 7. So right here, 2 to the 7th, we're going to add up 1, 7, 21, 35, 35, 21, 7, and 1. And we should end up getting 128 like we were expecting to. And that's that. Right? So it's not so much about getting the number itself. I mean, it does help us get the number itself, but it's really about what are we adding up to get there. And you'll see some questions like that. What numbers are we adding in order to get this? Cool. All right, another example, this is the binomial situation, is finding the expanded version of x plus y to the 0, x plus y to the first, x plus y squared, and so on. Well, again, we're going to kind of use this diagonal here to help us out. All right, same one that we just did. So when we find x plus y to the 0, well, we had just said anything to the 0 is going to be 1. So this one's kind of boring. But if we do x plus y to the first, this says, okay, you're going to use these coefficients here. So basically, right, anything to the first is just itself, x plus y. But what does this really mean? This means we have one x and one y. Right? So 1 and 1 are what we stole from here. It gets a little bit more interesting when we actually square this thing. So x plus y squared. We're going to take the, first of all, the coefficients here. So kind of like what we did for 1x and 1y. So there's going to be a 1, a 2, and a 1. And we just got to figure out what else goes in there. Well, we start with whatever this power is. So squared, that's going to go on the first term. So this is going to be 1x squared. And we have no y's. And then we're going to have this power go down by 1. So the next term is going to be x to the first, or just x. And then the next term is going to be x to the 0. And maybe I'll write those in so we've got them. So that's going to go down by 1. The y's are going to go the other way. The very last term is going to have the highest power. So y squared is going to be on the last term. Y to the first, so from 2 down to 1, and then down to 0, and I can include that as well actually over here, just to make sure we're extra clear on it. Right? And really though, the way this cleans it, you can absolutely leave it like that, that's fine. But we can also think about this like, okay, the 1 just has an x squared, right? Y to the 0 is 1, so that's fine. The next term is 2xy. And the last term is 1 times, well, x to the 0 is also 1, so we could just say 1y squared, or just y squared. So you can start with the biggest power and then work your way down from there. So we could do the same thing for x plus y to the third, x plus y to the fourth. Let's look at x plus y to the fifth, which is going to be right here. So this one we can say, okay, I'm going to start off with, I want my coefficients to be there. So this is, my first term is a 1. X is going to have the largest power, and y is going to start at 0. So I have all x's, no y's. And then for my next term, I look here and I say, okay, 5 is the next number in the row. So that's my coefficient. X should go down by 1, y should go up by 1. Then I go to the next term, 10. So that's going to be my coefficient. X will go down by 1, y will go up by 1. And so every time the sum of these powers, right, 5 plus 0, 4 plus 1, 3 plus 2, that should equal 5. It should be whatever this exponent is. All right, so we keep going. So the next number is also 10. X goes down by 1, y goes up by 1. Keep going. Next number is 5. X goes down by 1, y goes up by 1. And then the last number is 1. X goes down by 1, we really don't have any x's left, and y goes up by 1. So this is the sort of non-simplified version, and this is totally fine. If we wanted to leave it like this, that's absolutely fine. Of course, we could simplify some parts of this. So the first term we might just call x to the fifth. The next term we might say 5x to the fourth times y. Right, y to the first is just y. The next term we might say 10. Well, that one actually is exactly as it is. 10x cubed y squared. 10x squared y cubed, and I'm just running out of space, so I'm going below here. So 5x y to the fourth, right? X to the first is the same as x, and then plus y to the fifth. We could have 1 in there, but we don't necessarily need it. All right, so that's kind of the idea of that one. Let's look at a slightly more involved one. So this one's going to say, find the expanded version of 2x plus 4y cubed. Okay, well, first of all, we know that we are using this row, right? Because again, we look in the second diagonal, we see a 3 there, so cubed 3. So we're going to use this one. So these are our coefficients, right? That's the idea. These are going to be the coefficients. But we want to keep in mind 2x and 4y. Those also have coefficients on them, so we want to be really, really careful about this. So, okay, I'm going to take the first coefficient, 1, and I'm going to say this is getting multiplied by whatever the first term is. Before I didn't really need parentheses because it was just x, but now I'm going to use parentheses because it's 2x. So 2x is going to take the biggest power, 3. And 4y, again, I'm going to use parentheses. This is going to get the smallest power, 0. And then we're going to say, okay, I go to the next term. It should have a coefficient of 3 times, well, 2x, I'm going to bring that power down by 1. So I'm going to say squared. And 4y, I'm going to bring that power up by 1, so to the first. The next number is also 3. 2x, again, bring that power down by 1, so to the first. 4y, bring it up by 1, so square it. And then our last term, and I don't want to run out of space, so I might just put it under here. Our last term starts with a 1 as our coefficient. We've got 2x to the 0, right? We go down by 1, and then 4y, we go up by 1, so it's 4y cubed. Again, 3 plus 0, 2 plus 1, 1 plus 2, 0 plus 3. All of those sums of these exponents should be whatever our power is right here. And then we just clean this up a little bit. So a couple things to keep in mind, right? Anything to the 0 is just 1, so we can kind of get rid of that, right? We don't need that. It's just going to be multiplying by 1, which does not change anything. Then there are some other pieces like, well, if I take something to the first power, that's just itself. So we don't really need that exponent there. And then lastly, this one's kind of important. If you have 2x cubed, right, that means the 2 needs to get cubed and the x needs to get cubed. So both of those are going to get cubed. So here's how this is going to look. We're going to say, all right, the first term looks like 1. Okay, that doesn't do anything. Times 2 cubed times x cubed times 1. Okay, so that's fine. The next thing looks like 3. And then the square here we're going to distribute. So times 2 squared times x squared. And then we have times 4y to the first, but that's just going to be 4y. So times 4y. The next term is going to be 3 times 2x to the first. So okay, just 2x. Times 4y squared. So we know we're going to square the 4 and square the y. And then lastly, right, 1 times, okay, 4y cubed. So 4 cubed y cubed. This is a little bit ugly, so we're going to clean some of this stuff up just a bit. So we're going to say, okay, what is 2 cubed? It's 8. So this looks like 8x cubed. Then we have a bunch of numbers going on. So we have 3, 2 squared, and 4. Let's multiply all of those together. So 3 times 2 squared, which is 4. So 3 times 4 times 4 ends up being 48. And of course, you could just calculate that stuff. And then we have x squared and y, right? And then we do the same thing for the next term. We say, well, I have 3, I have 2, I have 4 squared. So 3 times 2 times 16. So 6 times 16 is 96. And then we have an x, and we have y squared. And then our very last term just has 4 cubed, which is 64 y cubed. So this would be the final version, right? It requires a little bit of cleaning up, and really, I would say the only new part of this, or well, not new part, but the only reminder part that we might need is some of those exponent rules. So you may want to practice a few of these. You'll definitely get practice in the homework and the on the project and so forth. But give a few of those a shot, and ask me if you've got questions.